Starting out, we're going to look at some vocabulary first. Okay, so ultimately, if we have a polynomial, each monomial in the sum we call a term. So if I take some random polynomial like 4x to the third plus 2x squared minus 5x plus 6, so if that's my function I'm going to be dealing with, okay, that is a polynomial function as defined earlier. And we could identify the degree and the leading coefficient at this point based on what we've learned so far. You know, the degree here is 3, the highest power term's power. The 4 is the leading coefficient. Okay? But ultimately, each of these individual monomial parts, okay, are considered terms. Okay? And when I have a polynomial function that's written from highest power down to lowest power, okay, we call that standard form. Okay? And generally, when we write a polynomial, we want to put it in standard form. Okay? The numbers in front of the letters, if you will, are the coefficients. And as we know, the 4 has a special name. It's not just the coefficient, it's the leading coefficient. Okay? And then in general, the 4x cubed altogether, that term, okay, we call that the leading term. So when we talk about these, I'm going to say that quite a bit, where I say a leading term or a leading coefficient, etc. Okay? So in our case, that 4x cubed would be the leading term. All right. Now, let's look at a couple of things that we're going to be doing with these polynomial functions that we're about to study. First of all, it says describe how to transform the graph of an appropriate monomial function into the graph of this. So we're going back to what we know about transformations. Okay, if we were to look at the parent function that this might come from, okay, the key issue here is that we're looking at the power. So if our original function here, f of x, was x to the fourth, okay, we might ask then, what did we do to x to the fourth to get to this new function? Well, let's start with the inside first. If we put this minus 2 in there, in the parentheses, okay, what is that going to create? What's it going to make the function do if I put a minus 2 in there? It's going to go 2 to the right. Okay, the negative out front is going to make it flip over the x-axis, and then finally the 5 will make it go up 5. So if we wanted to graph that new equation, if we started with the graph of the original equation, let's start with an xy chart for that. Okay, we know that 0, 0 is a point here. If we plug in a 0, we're going to get 0. Okay, 1, 1 is a point. Negative 1, 1 is a point. If I were to put a 2 in there, I'd get 16. Negative 2 would also give me 16. Okay, knowing that this is an even-powered function, the end behavior is going to be up in both directions, if you will. Okay, so there's a chart for that. And if we wanted to make a chart for our new function, h, okay, let's see if we can do that based on just what we know about transformations. So we said that this was going to create a situation where we're going to go 2 to the right. So these points that I'm just going to make corresponding points for all those by moving them 2 to the right. Okay, so I would move 2 to the right. I'd get 4, 3, 2, 1, and 0 would be my new x-coordinates if I wanted to develop a graph for this just based on the transformations only. And like I said, with any function, we can pick whatever x values we want to and we can plug them in and get an answer for it. But ultimately what I want to make sure we understand is that there's a relationship here between the points of this one and the points of this one. Okay, so with the y-coordinates, looking at that 16, okay, the first thing that would happen, like I said, we'd create a flip, so that would make it not 16, but what? Negative 16. Okay, and then we'd add 5 to that, which would make it go 5 up. So instead of negative 16, that corresponding point should be negative 11, shouldn't it? Similarly, if we do that with 1, 1 would become negative 1 first, and then if I go negative 1 plus 5, that's going to give me 4. Okay, and again, I'm looking at the y-coordinates only here. I already dealt with the x column. Okay, the 0 here, negative doesn't do anything to it, but going up 5 would make it be a just 5. And then the 1 and the 16 are nothing different is going to happen than what happened in the earlier part. Okay, so when we put our 1 in there, we're going to get 4 again, and then also negative 11. And think about why that makes sense in terms of what we just talked about with end behavior. If you look at this function now, there it seems to be a maximum point instead, and then going to the left and right, the numbers are getting smaller, aren't they? Okay, which should be the case, because what is that going to do to our original x to the 4th? It flips it. So doesn't that change the end behavior to the opposite way? Okay, so as we go off to the left and right, we should be getting smaller and smaller numbers. Okay, and again, if we graph that, if we look at the points that we have here, I'll keep this on here also. Okay. If you look at the points that we created, we had 4, negative 11, okay, which looks pretty reasonable on the graph that they have drawn, doesn't it? We have 3, 4. 3, 4 is right there. We have 2, 5. There it is right there, the new vertex, if you will. And 1, 4, and also 0, negative 11, and notice where that x-intercept or that y-intercept is. Okay. Okay. All right. We're going to look at some general graphs next of cubic functions. Okay. When we have a cubic function, we already talked about the end behavior. Being cubic means that it's in odd power, which means the end behavior is going to be one going down, one going up. So one possible shape, like our general cubic function, could be this. Okay, this one actually looks like it's stretched vertically a little bit, doesn't it? Okay. Okay, we also, depending on what the cubic function is like, depending on what the other terms are, okay, we might have a situation where we go up, down, and then back up, where we have a local maximum and a local minimum. Okay. And remember, for all these graphs, and when we draw them, we need to make sure that we put arrows on them also, as they continue. If we have a cubic function with a negative leading coefficient, then we have the opposite behavior in terms of end behavior. Okay. We could have, really, any of these graphs would be cubic functions. Okay. So when you see a cubic function, know that the graph is going to look like one of these types, depending on what the leading coefficient is, okay, and also depending on what the other terms are like. Okay. Similarly with the quartic function, okay, with our x to the 4th that we looked at, we know that that looks kind of similar to a parabola. It's a little bit flatter at the bottom generally. Okay. And then we also, though, could have this situation where we have coming down, up, back down, and then back up again. But notice, what is the end behavior like no matter which version I have? And they're both going up as we go from left and right. And again, these are just sample graphs. Does every quartic function look exactly like one of these? No, these are just samples, but they're going to have a similar shape to that. And if we have a negative leading coefficient, then of course, as we go left and right, we're going to go, instead of up, we're going to go down. Okay. All right, and again, these are just some sample pictures of some quartic functions. Okay, now here's a pretty important part to what we're going to do today, talking about local extreme values and zeros of polynomial functions. Okay? So anytime we have a polynomial function, okay, that has degree n, so whatever the degree is, it could be third degree or second degree or 10th degree, whatever it is, okay, it has at most n minus 1 local extreme values and at most n zeros. Now, to illustrate that, I want to go back to those two pictures that we just looked at. We're just going to, we can do this with any powered function that we want to, okay, but we're going to do it with a cubic function first, okay, and I want to illustrate both of those points. Okay, when I have a cubic function, that means that my n is equal to 3, and the highest power term would be cubic. That means the power is 3, and what the rule just said is that we have at most n minus 1 extreme values. So let's look at these pictures and see if that makes sense when we know that these are the general shapes that I would get when I have a cubic function. Okay, so n minus 1 extrema. So n minus 1 for us would be how many? 2. Okay, and if you look at this one has no extreme values. This one has how many? 2. It's got a maximum and a minimum. This one would have none. This one would have 2. Okay, so we have at most n minus 1 extreme values. Okay, so if you saw something like this, even though it has the right n behavior, okay, how would we know that that's not cubic? It's got 1, 2, 3, 4, 5, 6. It's got 6 extreme values. Okay, but a cubic function can only have at most how many? 2. Okay, n minus 1. So we know that even though it has a similar behavior at the ends, okay, this is not cubic because it has too many extreme values. Okay. All right, and then the other conjecture, or the other part of the rule says that we have at most n zeros. Okay, so at most n zeros. So in our particular case, our n is 3, so that means that we can have at most 3 zeros. If we look at this function right here, if we were to put this on a coordinate plane somewhere, at some point, it would have to cross the x-axis, wouldn't it? Okay, if you have n behavior that's up one way and down the other, wouldn't it have to cross the x-axis? Okay, so that one's going to have 1, 0. Okay, this one, depending on where I put the x-axis, if I put the x-axis down here, how many would it have? Yeah, it would only have 1. But if I put the x-axis here, it would have how many? It would have 3. And again, remember the key is that it can have at most 3 zeros. Okay. Same thing here. This one would have 1 for sure somewhere. Okay. This one, if I were to put the x-axis in the right spot, it could have 3. True? Or it could have down here or up here, it could have 1. Okay. What if I drew it like this though? What if I drew it so that that point right there touches the x-axis and essentially goes back? Okay. What would we count that as? It's got 1 right here, and then that would be, this would be a second one. One thing we're going to talk about in a little bit, though, is that one that where it touches and goes back, that actually counts for 2. Okay, we'll talk about that later, but still at most there are what? 3. Okay, still 3 at most. And we can talk about the same stuff when we deal with a quartic function. Okay, if I were to draw the x-axis on this one, right here, I'd have 1, 2, 3, 4 zeros, wouldn't I? Okay, but if I were to draw it down here, I would only have how many? 2. Okay, and again, what was the conjecture or the rule that we're using here is that we can have at most 4 zeros in this case because it's degree 4. So at most 4. Like I said, even though if I were to draw this picture for you, even though it has similar n behavior, how do I know that that's not a 4th degree function? Because it has too many extreme values. Okay, it's got 1, 2, 3, 4, 5, 6, 7 of them. Okay, and the only way I can have in a quartic function, I can have at most 3 extremes, okay, which means that that's way too many. Okay. Could we make a conjecture at this point at what degree this might be with 7 extreme values? It should be degree 8. It's got to be even because of the n behavior, right? So it's got to be even because of the n behavior, and it's got 7 extreme values, so a conjecture would be it's got to be 8. Okay, although does it have to be 8? What else could it be besides 8? Could be 10. Could be 12. Could it be 284? Sure. What about 285? No, it's got the wrong n behavior for that. Okay. All right. Questions so far? Okay. Now, we're going to talk next about this idea of a leading term test for polynomial n behavior. Earlier I put a function on the overhead about 4x cubed plus 2x squared plus 6x plus 3. I know it wasn't exactly that, but something like that. Okay, one question we might ask then, if this is our function and I want to know about its n behavior, okay, do I have to look at every individual function to know what the n behavior is going to be like? And the answer is no, okay, because ultimately this idea of a leading term test, if we just look at the leading term, okay, this cubic function is going to behave at infinity just like the leading term is going to behave. So we already know how the leading term behaves. It's a cubic function. That means it's got a behavior of up to the left and down to the right in some manner. We don't know what's going to go on near the origin, but we know the limit as x approaches infinity is infinity. Okay, the limit as x approaches negative infinity is negative infinity, and therefore this function is going to behave at infinity like the leading term. So all we have to really know is the degree of the polynomial, and we should be able to tell what the n behavior is like without even graphing it. Fair enough? Okay. So it doesn't matter what these terms are like. It doesn't matter if there's 3 more terms or 1 more term, or whether they're positive or negative, or what the powers are like. Okay. At infinity, okay, this function is going to behave like its leading term. Okay. So this is just one more slide to talk about our conjecture that we had when we have a greater than 0 and n is odd situation. Okay, again, it doesn't matter what else is behind it. If we have an odd degreed function, it's going to have that n behavior. Okay, if a is negative, it's going to have the opposite n behavior. It's going to go up to the left, down to the right. Okay. When we have a even powered function, same thing. Doesn't really matter what's in between. If we have that leading term being 4th degree or 6th degree or 284th degree, it's going to go up to the left, up to the right. If it is a negative leading coefficient, then it's going to go down in both directions as well. Okay. All right.